and welcome. This is Dr.BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the work energy equation for translation. The course outcome for today's session would be calculate the forces resulting in the movement of the connected bodies by using work energy equation involving springs. The topic covered would be work energy equation for translation. The topic learning outcome is understand the principles related to work, energy and power for solving the engineering problems. First, let us get a brief recall about the work energy equation and the system how the work and energy are involved for a given body. The work done equation which we have already seen is the product of force in the direction of the movement of the object and the distance the object has traveled. And the energy is nothing but the capacity to do work. So overall combined, now let us derive an equation for the object's movement because of the work done by the force involved in the system. Consider a body subjected to system of forces F1, F2 and so on and moving with an acceleration of A in x direction. Here this body is being considered and there are number of forces acting like F1 force, F2 force and F3 force having different magnitudes in different directions as shown here in the figure. And because of these forces that are acting in the system, it is given that we are assuming an acceleration of A. An acceleration of A has been achieved by this object. The initial velocity would be assumed as U. The initial velocity at A is being assumed as U. The procedure or the step where the object is placed here, object is at the starting point A, the initial velocity is being considered as U here. And the final velocity at B, that means when this object is moved or moving with an acceleration of A and it has reached at the position B, the final velocity when it reaches the point B is considered as V here when it moves to a distance S from the A to B. So the distance the object is moving because of the application of all the number of forces in the system is S. Let the resultant of the system of forces be R in the direction X. Okay. So because of all the forces that are acting F1, F2 and F3, what is happening to the body? The body has traveled to a distance of S in the direction of the force. So it has traveled to B, position B from point A, right? And the weight of the object W is also considered here, right? And let us consider the forces that are being acted, the resultant of all these three forces. Resultant of all these three forces is R. And because of this resultant, we are considering that is the application of the forces. Let the object has moved to an elementary distance ds. Okay, not completely to a distance of s here. What we are considering is it is moving in this direction and it has achieved a small elemental distance from here to here to a elemental distance of ds because of the application of the forces F1, F2 and F3. So that is what can be considered in this topic for achieving the work energy equation. Now we have force is equal to mass into acceleration. As we have discussed, the force equation would be the product of mass and acceleration. So here the force term which we are considering is the resultant of the three forces that are acting in the system, right? We have considered the resultant of the three forces which are acting F1, F2 and F3. The three forces that are acting in the system, we have considered the resultant at a time, right? Resultant is the force which replaces the forces that are acting in the system. so that the effect on the body will be same as if the number of forces are acting. And the mass is being considered as small letter m, and the acceleration as a, which is being achieved by the object. So here what we are writing is this mass m is being converted to w by g. So that representation is w by g into a. Whereas this acceleration is treated as rate of change of velocity, right? Rate of change of velocity. So that velocity change is treated as dv, and the rate at which this velocity change is happening is considered as dt. So the acceleration is the term which can be written as dv by dt. So that is the term it has been replaced with, is written here dv by dt. So at the end we can consider that the value of the force has been written as w by g into dv by dt. Now for calculating the work done by the all the forces in the system, for calculating the work done, the value can be given as r, which is the resultant of all the three forces, and the distance to which it is moving, that is ds. Initially we are considering that the movement of the object or the movement of the body is happening to a distance of ds. So the value of r here is being considered as m into dv by dt. So this value has been applied here, m into dv by dt into s or into ds. So this r has been written as m into dv by dt from this equation. So further simplification, this dv is being moved to right side, and it has been written as this ds is moved to the left side, and we are writing this as ds by dt into dv, which is shown here, m into ds by dt into dv. Further, this ds by dt term is rate of change of speed or rate of change of distance, right? Rate of change of displacement or distance, which is the velocity, So ultimately we will be getting the value of mv into dv. In this way, the work done by the three forces in the system has been obtained as m into v into dv. Now what we are doing is we are integrating the both sides of the above equation, which will imply the term r into integral 0 to s for obtaining the total distance that is being the object is being traveled, that is from the position 0 to s into ds, and m from this m into integral u to v, that is the initial velocity of the object because of the application of all the forces is u, and the final velocity is v at point b, right? So we are integrating that with v into dv. So when you simplify this further, you will be obtaining r into s, that is this integral 0 to s ds can be obtained as r into s, and is equal to m into v square by 2 u to v. And further simplification of these integral values, we can obtain r into s is equal to 1 by 2 m into v square minus u square, or we can write w by 2g v square minus u square. This equation is termed as the work energy equation. If you observe here carefully, this is the work done. This is the work done, work in the left hand side, and this is the change in kinetic energy. Okay, how this is change in kinetic energy? It is half mv square minus half mu square, where half mv square is the final kinetic energy and half mu square is the initial kinetic energy. So that can be treated as change in kinetic energy. So ultimately, we can say that work done or work is equal to change in energy. Change in energy. So this is how the work energy equation for translation is being represented. This is what the work done is equal to change in kinetic energy is the equation related as work energy equation. Now coming to the concept of connecting bodies or connected bodies. When in the previous case, we have seen the case of a single body on which the number of forces are acting and the object is moved to certain distance, and how the kinetic energy is equal to work done has been represented. Now, when number of bodies are involved in the system, when two or more number of bodies which are connected with each other by some means, let us say a wire or a string or any bar or by any means, then how to represent or how to consider the system, how to consider the work energy equation for that particular case. That we are going to see now. In connected body systems, what we do is sum of work done by forces acting on bodies is equal to the sum of change in kinetic energy of the bodies. That means we are going to consider the work energy equation of all the bodies in the system at a time. All the bodies in the system at a time. Let us say there are number of bodies that are involved in the system. There are number of bodies that are involved. This is a system and there are a number of bodies involved. And all these bodies are interconnected. All these bodies are interconnected. Now, for this situation, body 1, 2 and 3, for this particular situation, we are not going to consider the individual bodies and calculate the thing, but we are going to consider all the bodies at a time in the system for 1, 2 and 3. And then what we are going to do, the left hand side LHS is equal to RHS, where LHS is related to the work done and RHS is related to the energy. So what we will do, we will take the sum of work done. Sum of work done by all the forces. Sum of work done by all the forces in the system. Right? And how we will be considering all the forces? The forces that are needed to be considered here are the forces which are reason or cause for the movement of the object in the direction of the force. That forces only we need to consider, right? So as we have discussed previously, when the object is being moved to certain distance, the force that are involved or responsible for the movement of the object in that particular direction, that force alone we will consider. Okay, so that force will be taken and the distance to which the object is moved will be considered again. And do remember, as this is a connected system, all the bodies will be moving to a regular same distance, right? If this body 1, 2 and 3, some force is acting and the total system has been moved, then what happens? Let us say this object is moved to 1 meter distance, then as this is a connected system, this second object will also move to 1 meter. And similarly, first object will also move to 1 meter. That's the reason we will be considering the forces which are involved in the system for the objects to move in a particular direction, that the distance to which they are moving combinedly. So we will be considering F1 plus F2 plus F3 and so on into the same distance which the object is moving. Okay, this is how we will be considering the case. Is equal to, again, the change in velocity, rate of change of velocity, the kinetic energy. So initial kinetic energy and final kinetic energy will be considered, and this will be taken as the summation. This will be taken as the summation for obtaining the values. So whenever we are going to consider the system which is having the connected bodies, which is having the connected bodies, all the bodies will be considered at a time. So let us take this example here. Here in this example, there are two bodies, body A and body B. We can say block A and block B, which are connected using this string, over this pulley. Okay, and because of this application, in this system, there are two bodies present, two blocks present. For this system, if we need to apply some work energy equation, then what we need to do? We need to consider both the bodies at a time, LHS and RHS, both the bodies at a time, and the movement. Let us say the objects are moving in this direction, and the movement which the objects are making in that direction, what are the forces that are involved? That forces will be considered, and the displacement to which the objects are moving will be taken. Okay, so both the bodies will be combined at a time. That's the case how we should be considering the system. So this is about the work energy equation in translation and the connected body system. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.